What's up, folks? So today I'm going to discuss the architecture for a joint image text rectified flow model. And yeah, let's just jump right in instead of me giving you the whole preamble. I was going to do a text conditioned image model first, but I think I want to just jump straight to the joint image text model. So let's just jump right into the diagram. I just made this using Draw.io, and then let's switch to my iPad. So, okay. So we're doing a joint generative model. So this is the modeling objective. We have a image distribution and a data distribution, and we want to model the joint distribution, right? So we have an image and text describing the image, right? Like what does that joint distribution look like? So the ultimate goal for this model is we're going to output text velocity and an image velocity such that when we perform inference, we can generate an image. We can generate an image and its accompanying text caption. So the loss function, right? Originally, we just had this. We had an image head that produces v hat, right? In our last video. And then we calculate v star by taking x1 minus x0, right? And then we just minimize this expectation. Now, the only difference is we're just going to add the squared L2 norm for the text, right? So we have v hat text, and we calculate v star text with the, x text 1 minus x text 0, right? And then we just minimize the sum of the two squared L2 norms, right? And then last time our expectation under the distribution of x image 0, x image t, and t image. Now the only difference is we're going to sample text for time. So we're going to sample noise for text. We're going to sample text time for text, and then we're going to corrupt our sample to x text t. So we have a legend down here. DR is going to be double ResNet block. DS is going to stand for a downsample operation, and SA is self-attention, and proj is projection layer. Okay, so what this architecture looks like is, so we have our training data, which is image caption pairs, right? So we have an image distribution and a text distribution. Maybe I should have made these overlapping to show that they're not independent, they're joint. Well, I guess, yeah, that's why I put them inside of here, to show that they're part of a joint distribution. So we have the image path, right? We sample x image 0, so we sample an image from our image distribution, right? And then we sample a time here. And then we corrupt the image by passing in the time to calculate x image t. That's going to come out of here. And then we pass that into our UNet, okay? And then that goes through double ResNet blocks, downsampling blocks, and self-attention. I don't think I had self-attention in the last video, but I'm adding self-attention in this video, or in this architecture. That's the only difference. But we make the channels go from 128 to 1024. I might drop those channels to 512. Actually, I'm not. I did drop the channels to 512 in my personal run, and it prevented overfitting, and it made the validation curve a lot smoother. But that was actually image only. So now that we have text, anyways, we'll see. Okay, so then we send it to the middle layer, and then we're gonna we're gonna do film and cross attention with the text path. Also, the image time we send into this time embedding here, right? And we're gonna fuse that with the text time and then projected it into each of these layers, okay? So for the text path, we sample, so, okay, we have a image caption pair, right? So we sample an image caption pair, right? We sample an image and a caption together, right? And the image we send into the image path, and the text, the caption, we send into Flan T5. So we're gonna use Flan T5. Flan T5 is essentially an encoder decoder model that uses transformer architecture, and it's instruction tuned. Well, Flan T5 is the instruction tuned version of T5. I'm not going to go into the details really in this video. I mean, if you want, you can look it up yourself, but essentially all you need to know is that it's an encoder, it's a transformer based encoder decoder model that outputs a latent. You pass in text and it outputs a latent. And then if you input that latent here, the decoder will autoregressively decode that latent into text, right? So you can put in a latent of a fixed size, and it decodes a sentence embedding a sentence of, or a token embedding of arbitrary size, right? It basically decodes until it hits the end token. So Flan T5 has a pre-trained latent space. So what happens is when we sample in an image caption pair and we send the caption into Flan T5, right? We put it into the Flan T5 latent space, okay? And then we sample the time, right? So we sample text 0, we sample time, T text, right? And then we corrupt to get X text T that comes out of here, right? And then we can pass that into the cross attention layer, right? And then we also pool the text. So we basically do some kind of pooling. We average it to create a global embedding, a global text embedding, and we do what's called film. So the way film works is, I think high level is just we are pooling the text to create a global text embedding, and we use that global text embedding to modulate the image features in the mid block. Okay, so we calculate the image features in the mid block, which is going to be 1024 features, and then we modulate them with the global embeddings. And modulation means essentially we apply an affine transform, stretching, compression, right? So, right. So we modulate the image features, and then we pass those modulated image features into the cross attention block. So we perform cross attention between the modulated image features and the text tokens. Okay. So the text conditioning is coming from film, and it's coming from cross attention. It's coming from cross attention the most, but it's also coming, we're getting a bit of global text. We're modulating the image features using global text before we pass it into the cross attention block. Okay, so, right, and then we decode. And we create a separate text head in this case. Originally we had only an image head, now we just output a separate text head. Okay, and then once we have our image and our text velocities, for the text, when we have an right, so we know how to, we did inference last time for the image velocity, right? We simply, start with noise, and then we perform inference until we essentially transport the noise to the image distribution in pixel space. Now for the text, we do the same. We sample noise, and then we perform inference, and we transport it all the way to we transport it all the way to the FLAN T5 latent distribution, right? And then we pass that resulting latent into the FLAN T5 decoder, and it gives us an output string. So in this way, we can see this is a very powerful model. So I don't know if I mentioned this, but I'm not the first one to do this, of course, right? Like there's a 2025 paper called OmniFlow where they have, I think they have video, audio. It's a joint video, audio, text, and image rectified flow model, right? So it's much more advanced than this, but I think it came out June or July of 2025 of this year. But this is sort of a toy representation of that model, right? Which is a very good thing to work through if you want to be an expert at machine learning, if you really want to understand these architectures. So the reason why this model is powerful is you can, right? So if you're modeling image and text jointly, right, then you can start with an image, right? Let's say you can start with an image and then you can flow a noisy text embedding towards the text that matches that image. So you can caption an image, or if you wanted to, you could start with text and flow an image and flow a noise towards the image distribution, right? So you can use text to generate an image, right? So you can not only caption images, but you can also generate images from text. It's super powerful. This is a really cool model. So yeah, I think that just about explains it. So in the next video, we're gonna look at this diagram, and then I'm gonna take the code that I already coded for the last image rectified flow model, and I'm going to add the components necessary to produce this joint image text, to model this joint image text distribution. Okay, I think that's it for this video. Thanks for watching.